Okay, this is part 2 of the Precalculus final review notes. This overlaps a little bit with part 1, so you can skip ahead if you've already seen this part. So graphing quadratics, this is there's two forms here. We've got on the right, this is called what? This is called standard form, f of x equals ax squared plus bx plus c. And on the left, we have vertex form. So that's f of x equals a x minus h squared plus k. So definitely I would put these on the note card. So this vertex form is easy because it easily gives you the vertex, right? What's our vertex going to be here? It's going to be 5 comma negative 7, just based because this is h comma k, right? H comma k is your vertex. Okay, we're subtracting, so it's still 5. We're subtracting, and the k, okay, it's minus 7, so 5, negative 7. So graphing that, it's pretty straightforward. If you were just doing a rough sketch, a good point to then try is just one of the x values adjacent to that vertex, so like a 6. So if we just find f of 6, we'll get 1 squared times 2, we get negative 5. So then from those 2 points, we can draw a rough sketch of what this parabola will look like. Okay. On the right side, when we have standard form, to get the vertex, it is negative b over 2a, comma f of negative b over 2a. Okay? So negative b over 2a here, that's going to be 6 over 6. That's 1. And then we'll plug the 1 in to get the y value. We'll get 3 minus 6 plus 2. That is negative 1. So 1, negative 1 is my vertex. And then same thing as the other side, like plug in a 0. Like plug in a 0 to get a good, another point. So f of 0 is 2. And then I can sort of get a rough sketch from there. Okay? Good on that? So getting the vertex, either negative b over 2a, f of negative b over 2a, or h comma k, and I plug in a couple points to get a sketch. Okay? Points to graph. Find the equation of a quadratic whose vertex is negative 1, 1, and contains a point 3, negative 2. So if we're given the vertex and a point, we want to use that vertex form. F of x equals a x minus h squared plus k. Because we know what h and k are, right? H and k are negative 1 and 1. So we know that this is going to be x plus 1 squared plus 1. You follow me? Yeah. So the other thing we know is that we know that there's a point, 3, negative 2. So we have 3 unknowns right now, right? F of x is unknown, a is unknown, and x is unknown. But we do know that 3, negative 2 is a point. So we can say that negative 2 equals a 3 plus 1 squared plus 1, and then we can just solve that for a. So we're going to get negative 3 equals 16a, and so negative 3 over 16 equals a. So then my function would be f of x equals negative 3 over 16 x plus 1 squared plus 1. Okay? Good? Can I turn the page, or we need a minute? Okay. Okay. All right. We've done that. We've done describe a function. Is this? Yeah, that was page 8. We're on page 9. We're on rational functions. Okay. Rational functions. So rational functions are a polynomial over a polynomial. So p of x over q of x, where an example could be, x squared plus 1 over 3x to the third minus 1, right? That's an example of a rational function. There are features of a rational function that help us graph it and understand how the function looks. The first is the y-intercept. Y-intercept's easy. All you do is plug in a what? Plug in, to get the y-intercept, you just plug in a 0. That's it. That's it. Plug in a 0. You get the y-intercept.
Most of them don't have it, right?
Sometimes they don't have it if they have a vertical asymptote there. So, yeah. But if you can plug in a 0 and you get a value, you'll get a y-intercept. X-intercepts, you want to set the numerator equal to 0. And you ignore the holes. And we'll talk about that in a moment. For vertical asymptotes, that's when not the numerator is 0, but when the denominator is 0. And again, you ignore the holes. Horizontal asymptotes, we just did this. So this is the same as when limits go to what? Limit goes to infinity, right? You're seeing what the behavior of the graph is as x approaches really big numbers. And so we have the 3 situations. Do you remember the 3 situations? We have top heavy, bottom heavy, and then a tie, right? So if it's top heavy, something like x to the third over x squared, it's going to be none, right? There is no horizontal asymptote. If it's bottom heavy, something like x squared over x cubed, that's going to be 0. And if it's a tie, something like 3x squared over 2x squared, it's the ratio of their coefficients, so 3 over 2.
So one difference from this limit is top is not infinity?
Yeah, so the limit is infinity. So if the limit is infinity, then there's no horizontal asymptote. So horizontal asymptotes only happen when the limit as x goes to infinity is a specific value, like 0 or 3/2, a specific number. If the limit is infinity, there is no horizontal asymptote.
What does that say next to where it says set denominator equal to 0?
Ignore holes. So now we'll talk about holes. Do you guys remember this a little bit? We just did this with limits. Remember when we took limits and you would get 0 over 0? That would indicate that there's a hole, right? So it's when a factor exists, something like... Mm-hmm. When you have a factor top and bottom, like something like this.
They can't help.
Yeah, so we have a hole here at what x value? Not 1, but at -1. X equals -1 is a hole because it makes both top and bottom 0. So we cancel the hole out. To get the y value of the hole, what do you do with this x value? It's just like limits. You remember this? You plug it into what's left. So it would be -1 minus 2, that's -3 on top, -1 minus 1, -2 on bottom. So it would be double negative, so it would be 3 over 2.
Wait, so anything that cancels top and bottom is a hole?
Correct. The hole is the 0 of that factor. Does that make sense? So the hole is not 1, the hole is -1 because that makes both those factors 0. When we graph, you want to find features above, basically, and then draw a number line for behavior. And that's where you write out like the x-intercepts and the vertical asymptotes on the number line, and then you test points. Do you remember that a little bit? Remember doing that? Like I'll do an example in a moment, but you put the x-intercepts and vertical asymptotes on a number line and you test points in between, and then you sketch from there. That's how, we'll do some examples of that. That's a little rusty. Can I turn a page?
Yeah.
All right, no problem. All right, I think we're good. All right, so now we have some examples. All right, so we're going to go through that kind of checklist. Given a rational function, first thing we're going to do is try and get the y-intercept. So f of 0 is, in this case, 0 over -4, so it's just 0. So we have a y-intercept and an x-intercept at 0, 0. Okay, that's the first thing I did. That's the y-intercept. Next, we can get the x-intercept by setting the numerator equal to 0, but we already found what the x-intercept was. It's 0, so we're already good on that. So f of 0 was 0. So that is both the y-intercept and it's also an x-intercept because the y value is 0 and the x value is 0. That would be to get the x-intercept, you set the numerator equal to 0. You also get 0. So that's like these two are the same thing. The y-intercept and the x-intercept are the same thing. Does that make sense? Okay. Then you always want to factor the rational expression. So we're going to get 2x on top, and then factors of x squared minus 4 are x plus 2, x minus 2.
Those are your actual,
Right. So do we have any holes here? No, because there's no pair top and bottom. It's all on the bottom. So that means we have vertical asymptotes at what points? But what x values? We said the denominator equal to 0, so it would be at x equals negative 2 for the first one and x equals 2 for the second. Okay? You follow that? The horizontal asymptote, we check the degree top and bottom, which is it's bottom heavy, it tells us in the question. So that means the horizontal asymptote will be at where? At y equals 0. Good. Okay, so now we got all these features. We're going to go ahead and plot them down below. So we got that horizontal asymptote at 0. We got a vertical asymptote at 2. We got a vertical asymptote at negative 2. So that's all we have. We have these two vertical asymptotes, a horizontal asymptote, and this x-intercept in the middle, and the y-intercept in the middle. But we don't really know how the function looks, right? You couldn't really draw it from just this information, correct? This is where the number line comes in. So the number line, you draw it out, and you put all the x-intercepts and vertical asymptotes on it. So we're going to have 0 on it, we're going to have negative 2 on it, and we're going to have 2 on it. And what you're going to do is you're going to try a value outside and in between each of these points. So give me a number above 2. Any number above 2. 3. So plug a 3 in, we're going to get 6 over 5. That's a positive number. That means everywhere from 2 and above, it has to be a positive number. So because it has to be a positive number, we can then draw it. I can draw it because I know as it approaches this vertical asymptote, it has to approach positive infinity, because that's the rule about approaching asymptotes. They have to approach positive infinity or negative infinity, and because it's a positive number, it must approach positive infinity. And as I go to the right, because I have a horizontal asymptote at 0, it must approach that. Does that make sense?
Yeah.
How about between 0 and 2? So give me a number between 0 and 2. 1. So let's plug in a 1. Okay. Plug in a 1. What do we get? We get 2 over negative 2. That's a negative number. So that means it's going to approach negative infinity. Does that make sense? Am I rushing that? And then plug in, so this is negative here. A number between negative 2 and 0 is negative 1. That's going to be a positive value here, so that means it's going to go up here. And then a number negative 2 or below, negative 3, you're going to get negative again. So it's going to look like this. Okay? Do those steps make sense? And I think the hardest part is going from the number line to the drawing. Like, do you understand? Like, I think that's what my last class kind of struggled with. Does that make sense? Do you get how, because you know the behavior at the asymptotes and you know it's positive, you know it has to go to positive infinity or to, yeah. Go ahead, Ryan.
Can you do a chart like this?
Sure.
Instead of the number line?
Yeah. I don't care about the number line itself. Whatever method you have to figure this out is fine, but the number line is just like a helpful way. And this also reappears in calculus too, the number line stuff. Okay, let's do the next one. Factor top and bottom, x plus 1, x minus 1. On the bottom, factors are x plus 1, x plus 1. Okay, let's get the the y-intercept, plug in a 0. We're going to get negative 1 over 4, which is just, sorry. We're going to get negative 1 over 1. I'm going crazy. We're going to get negative 1 over 1, which is just negative 1. So I can go ahead and plot that y-intercept there. Here now, this is a weird problem because We do have a hole, right? See, we have a hole at what value? -1. This is a weird problem because yes, we have a hole at -1, so I could cancel these two out. But when I plug that -1 back in, do I get a value? No, because there's also a vertical asymptote at -1. Even though it appears top and bottom as a pair, you'd think, oh, we have a hole at -1. But because x plus 1 appears an extra time in the denominator, that kind of like beats, quote unquote, the hole. And so really we have a vertical asymptote because you would get -2/0. So it's undefined it's like not a point, right? The hole is undefined. And that's because really we have a vertical asymptote at that point. So if you get a hole, but you plug in the number and it's still undefined, it's not a hole, it's a vertical asymptote. Does that make sense? So we can draw that. Any other piece of information here? I mean, there is an x-intercept, right? I can set the numerator equal to 0 and ignore the holes, and I would get 1, right? X equals 1 is an x-intercept. So we have 2 points and a vertical asymptote, and then we also have a horizontal asymptote at where the degrees are even. So we take the ratio of their coefficients. It's going to be at y equals 1. Okay, there we go. And from here we actually know what this one's going to look like, at least on the right side, because these 2 points have to connect. It's going to go to -infinity here, and it's going to approach 1 from the bottom here. That's pretty straightforward. On the left side, I guess like we're not sure if it's going to be on the bottom or the top, so we can test the number. So like any number below -1 we can test, so like a -5. Plug in a -5, you're going to get positive on top, and you're going to get a positive on bottom. Yes, you're going to get a positive on bottom, so this must be positive. Okay. How do you know this one's negative? You know it's negative because we have these 2 points and we have to connect those 2 dots. And like, do you see what I'm saying? And it can't cross the x-axis again, and it has to approach those horizontal and vertical asymptotes. On the left side, we're not sure if it's going to be above or below this, but if we plug in a -4 or any of these values into here, you'll see that it's a positive number in this quadrant, and therefore it must look like this. Okay, so one more. Same thing. F of 0, plug it in, we get 2/3. Okay, right here. Let's factor top and bottom. We're going to get x plus 1, x plus 2 over x plus 3. Any holes? No holes, but we're going to have a vertical asymptote at x equals -3, and we're going to have x-intercepts at x equals -1 and x equals -2. Right? I'm just setting the numerator and denominator equal to 0. So let's go ahead and plot those. We're going to have -1, we're going to have -2, and then we're going to have a vertical asymptote at -3. And there is no horizontal asymptote. How do you end up with 2 x-intercepts? Yeah. So because we got x plus 1 and x plus 2 in the numerator, you're going to set the whole numerator equal to 0. So -1 can make it equal 0, or -2 can make it equal 0. That's why we have 2 x-intercepts. And then we have 1 vertical asymptote because you set the denominator equal to 0, and that's -3. What's up, Brian? The slant asymptote?
Yeah.
You don't have to worry about slant asymptote. It's okay. But yeah, that is correct. So now number line it. We're going to have on the number line -1, -2, and -3. Test a point above -1, like 100. We're going to get positive. So you can see that above -1, it's going to go to up to infinity like that. Between 1 and -2, so we plug in a -1.5, we're going to get a negative output here, so that means it's going to dip below. And then between -2 and -3, we're going to get a positive output here, so it's going to go straight up. And then if we test something below -3, it's going to be negative. So that means it has to approach negative infinity here. And it can't cross the x-axis again, so it also must be pointing downward to the left. Okay. So I on the test, and you'll get a practice test next week. Like the rational function question will be straightforward. It will be following these steps: y-intercept, x-intercept, vertical asymptote, horizontal asymptotes. Label them, and then sketch. Right, that's what we're looking for. But I'm not looking to trick you. I'm looking to assess you in a straightforward way on these. Okay. All right. Chapter 3 review. Are we good on this? Can I move on?
Yeah.
Okay. Graphing exponentials. All right. So form of exponentials, we have f of x equals a times b to the x. If the absolute value of b is greater than 1, that means it's going to be what? What kind of exponential? It's going to be growth. And if the absolute value of b is less than 1, it's going to be decay. Okay? So, here we go. What's this going to look like? Well, we can plug in a 0 for x. If we plug in a 0 for x, we'll get our starting location, 2, right? Because 3 to the 0 is 1. 1 times 2 is 2, so 0, 2. That is our y-intercept. And then we can just, we plug in a 1, right? So 3 to the 1 is 3, times 2 is 6. And we can create a curve from there, right? This is 1, 6. On the right side, it's decay, so it's going to be decreasing, but we can follow the same steps. Plug in a 0, we're going to get the same y-intercept at 0, 2. But when we plug in a 1, we'll get 2/3, so it's decreasing. It's it's reflected around the y-axis versus growth. Okay, good. Can I move on? All right. So what about when you're given 2 points and you want to create the equation? So we know f of x equals a times b to the x, and we know a is the y-intercept. Okay, what's your y-intercept? It's given to you here. What's the y-intercept? It's right here. It's 2. So that means a must be 2, right? A is the y-intercept. A must be 2. So we really know that this is f of x equals 2 times some b to the x. So we have 3 unknowns, f of x, b, and x. How do we solve for b? Well, we know another pair of coordinates, 2, 4.5. So that means that 4.5 must equal 2 times b to the 2. Follow me? You're plugging in y and x. Divide both sides by 2, 2.25 equals b squared. Root both sides, 1.5 must equal b. Okay, so your formula is f of x equals a times 1.5. F of x must be 2 times 1.5 to the x. Okay?
Why do you choose that one?
Because that's the only other point given to you. If you plug in 0, 2, you can't find b because b just becomes 1. Does that make sense? If you plugged in 0 and 2 here, b would be to the 0 power, and that would just become 1. So it wouldn't allow us to find b. Okay, logs.
It doesn't matter about plus and minus.
No, so b is always positive in exponential functions. B is always positive. All right, evaluating logs. Do you guys remember logs a little bit?
Yeah.
So what is log 5/625? What does that mean?
5 to the power of something is 25.
Yeah, so this is the exponent of 5 that would make 625. So 5 to what power is 625? Anybody know? So I think it is 4. Because 5 times 5 is 25, times another 5 is 125, times another 5 is 625.
Only graph calculated that.
No, in the test, the logs will be straightforward that you can either leave them in exact form or you'll be able to figure it out using a regular 4-function calculator. I mean, worst case scenario, you just do 5 times 5 until you reach 625, right? And then you'll know, oh, okay, that's 4. What about this one? Natural log, let's go for a second. What does ln mean? What does ln mean?
Log base E.
It means log base E. And if you just see a wild log flying out in the wild, what base is log? Like 10. Good. So this is saying e to what power is the square root of e to the third? What is that?
3 over 2.
It's 3 over 2. Does that make sense? Because this is really e to the 3 halves. So, okay, that means that e to the 3 halves would be e to the 3 halves. The answer is just 3 halves. Okay? Rewriting in exponential form. We already did this. This is the equivalent of 4 to the thirds equals 64. And over here, this would be log base 5, 25 equals 2. So logs are the inverse of exponentials. Instead of giving you the output, it's asking for the input. It's asking for the power. That's what you're going for. Okay, expanding logs. When we multiply, we add. So this is the equivalent of log x squared plus log y minus log root z. Okay, so when we multiply inside a log, we can rewrite that as addition. When we divide, we can rewrite that as subtraction. When you have powers on a term inside a log, you can put that outside the log. So log 2x plus log y minus 1/2 log z. Okay? To condense logs, it's the same, but just in reverse. Okay? So let's add these together, right? Let's add these together. This is going to be log base 2 y to the 1/3 z, right? You follow that? And then we're going to subtract this, so we're going to have log x squared over y to the 1/3 z. Okay?
Isn't that z positive, so wouldn't that go up on top with, wouldn't it be x squared z on top? Isn't it on the positive side?
Hang on, let me pause for a second. Yeah. We're just going to keep going here. All right, financial fun, yeah. All right, so there's 2 equations. You can, obviously put these in your note card. We have discrete and we have continuous. So we have future value, I'll label this in a second, equals the principal times 1 plus r over n to the nt. So this is future value. This is principal. This is like your interest rate. This is like compounding period. Compounding frequency, not period. Compounding frequency per year. This is years. Okay. And then we have, if it's continuous, anybody remember continuous? It's similar. F equals PERT. P-E to the RT. Okay? Good on those?
Yeah.
So if we put 100K in an account for 20 years and has 11% interest, how much will we have as compounded monthly? So your future value will be equal to that principal, 100K, times 1 plus your interest rate, 0.11. We're compounding monthly, so what's the frequency per year? How many times per year? If it's monthly, it's 12 times to the power of 12 times 20. That's it.
What did you put on the top?
0.11, 0.11. If it's compounded continuously, it would be 100K times e to the 0.11 times 20. And you can just leave it in exact form. You don't need to evaluate that. It's fine to leave it in exact form. When we have $1 million, so that means that you know the future value, but what's unknown here, if it's asking when, we don't know how many years. So 1 million equals 100,000 e to the 0.11 times t. And then we're going to solve for t. So first step here would be to divide both sides by 100k. And so we'd get 10 equals e to the 0.11 t. And then to undo an exponential, what do we do to both sides? We take the natural the natural log. ln 10 equals 0.11 t. And then divide both sides by 0.11. Divide by 0.11. Scratch it. So t equals ln 10 over 0.11. Should I pause for a moment here?
Yeah.
Okay. All right. Okay. So here's some like common log equations and exponential equations. One way to solve exponential equations. There's two ways to do it. One way is you make the base the same. So 1 over 5. Can we rewrite that in the same base as 5? 1 over 5 is the same as 5 to what power? Is my question. Yeah. So if this is 5 to the x equals 5 to the negative 5 to the negative 1, that means that what is what? X equals negative 1. That easy. Okay? Can 1296 be rewritten in terms of base 6? It can. Anyone? Anyone? What power? It's power. Okay. Are we sure about that?
Yeah.
Okay. Okay. Sorry. I just want to make sure. All right. X equals 4. And this one, 2 to the 16. 6 to the power of what is 2 to 16? Yeah.
3.
3. So that means.
Or wait, no, sorry, 4. 4.
Well, how could that be? How could that be 4 if that's 4?
3 is 2, 1.
The x would be 5. X is 5.
What 6 to what is 216? If 6 to the 4th is that can't be.
6 to the 3.
Well, 6 squared is 36. 36 times 6, 216. Okay, yeah. So that means 2x minus 7 must equal 3, and then x equals 5.
Yeah.
Okay, good. Are we following so far? You just make the base the same, and then you solve. You set the exponents equal to each other and solve. If we can't do that right here, see how 49, like we cannot write that in terms of base 5. What do we do with both sides? We take the log of both sides. So log, when we take the log of base 5 of both sides, that undoes the exponential. So we just end up with 3x minus 1 equals log base 5, 49. And then we solve for x from there. Okay? So then 3x equals log 49 plus 1, and just divide by 3, that's it. Okay?
Is that log base 5?
Yeah, it's log base 5. Because the base has to match whatever the exponential was. Okay, 10 to the x plus 5 equals 125. Again, we cannot rewrite it in this case. So we take the log of both sides. And so x plus 5 equals log 125. Remember, just a wild log is log base 10. So x equals log 125 minus 5. Okay?
If you want a kid to learn, you gotta catch his freaking
Say again? Yeah.
Pause for a second.
Yeah.
Are you supposed to do the other ones?
Say again?
Are we supposed to do the other ones on our own?
I'll do the other ones. I'm just waiting. Yeah, I can do them. So, same thing here. Natural log both sides. We're going to get x equals ln 34. Here, before we natural log, we're going to divide by 3 first. We get e to the x equals 40. So x equals ln 40. Same thing here. Going to add the 8. E to the x equals 59. X equals ln 59. Ln x equals 2.5. That means e to the 2.5 equals x. Right? We're just rewriting the log as an exponential. Likewise here, this means e to the 2.8 equals 3x minus 2. And we're just going to x alone. So we'll get e to the 2.8 plus 2 equals 3x, and then we'll divide both sides by 3, and we have our answer. Okay?
So, okay.
Am I going too fast?
Yeah.
Just like that. So when it's written as a log, we can rewrite it as an exponential by putting the base to the power of what it equals and setting that equal to the input. So e to the 2.5 equals x. Here, e to the 2.8 equals 3x minus 2. And then we solve for x. And in this last one, well, this is kind of a gimme. We have ln of e to the x. So by definition, what does ln of e to the x have to be? When you take the ln of e to a power, it just becomes the whatever the power is. Because remember, this is saying e to what power is e to the x? E to what power is e to the x? X. So it has to be x. So this is really just saying 2x equals 5, or x equals 5 halves.
So if the base is the same as the number,
Yes.
then it just cancels out the log.
If the bases match, right? The base of the exponential and the base of the log match, they undo each other. All right. We're just going to keep on trucking. Good?
Unit circle.
Unit circle time. How are we on unit circle?
Okay.
Feeling good. This is so important.
Can't be on no card.
We're going to say no to the unit circle
Or no. Is it the
for
only
no
restriction?
card. That's the only restriction I have.
Because there'll be a question on the text.
Yeah, it's one of those things that's really important to know by heart. And so let's go over just briefly. If you're converting from degrees to radians, what do you do here? You multiply it by what? Remember? Anybody remember?
No idea.
180.
There's 180 involved. Pi over 180. There we go. Pi over 180. So this is 225 pi over 180, and we can simplify that. And then likewise, 3 over 4, if I'm converting to degrees, I multiply by 180 over pi. I think like a good way to remember is like you're canceling out the pi, right? And generally, radians are written with pi inside them. So we have 3 times 180 over 4. The pi's will cancel, and you simplify, right? Okay. Unit circle, first quadrant. How are we on this? Let's.
Yeah.
I can do the degree.
Can we do it? Can we just do it? You guys know it?
Do it.
Let's do degree. Do the degrees. What do we got?
Okay, 0.
Yep.
And then 30.
Yep.
And then 45.
Yep.
60.
Yep.
90.
Nice. Anybody can do the radians?
Yep.
August.
Pi over 6.
0 first, then pi over 6. Okay.
Okay. Pi
Then-
over 0, pi over 6, pi over 4, pi
Yep.
over 3,
Yep.
pi over 2.
Perfect. I messed that up. Pi over 2. Okay. Then the coordinates. The bottom we have here
0, 0. 1, 0. Sorry.
1, 0. Then
Root 3 over 2, 1 half.
root 3 over 2, 1 half. Then
Root 2 over 2, root 2 over 2.
root 2 over 2, root 2 over 2. And then,
Opposite of the 30.
1 half.
yeah, 1 half, root 3 over 2. And then at the top we have
1.
0, 1. Good. And remember that the x value, right, is the what and the y is the what. The x is the cosine and the y is the sine of the theta, right? Good?
Yeah.
All ASTC, all students take calculus, classes, whatever. This just means that like all the trig functions are positive here, the sine is positive here,
10.
the tan is positive here, and the cosine is positive here.
10 is sine over cosine?
Tan is sine over cosine.
Yeah.
Okay, so if we want to find, again, like, maybe we do the full unit circle before we do these 3 here.
We only have 5 minutes.
Okay, we can do the unit circle in 5 minutes.
Yeah.
Can you go back to the second?
Yeah.
Okay. Wait, does that little box, does that just show which one of those values is negative?
Which one's positive? So let me make that clear. Yeah. All are positive, sine's positive, tan's positive, or cosine's positive. Yeah. Good?
Great.
All right. Then we got the full unit circle. Let's speed run this. So, degrees. We go 0, 30, 45, 60, 90, 120, 135, 150, 180, 210, 225, 240, 270, 300, 330, sorry, not 330 is next, 315, then it's 330, then it's 360. Okay? Are we good on that?
Yeah.
For radians, we start at 0, then pi over 6, then pi over 4, then pi over 3, then pi over 2. I'm going to fill in the corner points. This is pi, this is 3 pi over 2. This is back to 2 pi. We add pi over 6 for the, quote, big slices. So we got pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, which is 2 pi over 3, 2 pi over 3. 5 pi over 6 is down here. Then we have pi. Then we have 7 pi over 6. Then we have 8 pi over 6, which is 4 pi over 3. We have 9 pi over 6, and we have 10 pi over 6, which is 5 pi over 3. Then we have 11 pi over 6. And then in the middle, pi over 4, pi over 2, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4. So for the radians, you just add pi over 6 for all the big slices. Like, you know what I mean by big slices, right?
Yeah.
Like, and then you add pi over 4 for like a big slice and a half. I think I don't know who it was. Was it Caston that was obsessed with the pizza slices? Yeah.
Yeah.
Does that say 7 pi over 4?
Yeah, down here is 7 pi over 4. So pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5, 6, 7 pi over 4. Okay, then coordinates, we got 1, 0, 0, 1, negative 1, 0, 0, negative 1. Then we've got root 3 over 2, 1 half, root 2 over 2, root 2 over 2, 1 half, root 3 over 2. And then it basically we just are mirroring this as we go around the circle. So this is root 3 over 2, root
Negative 1 over 2.
yeah, negative 1 over 2. This is root 2 over 2, negative root 2 over 2. This is 1 half y, and then negative root 3 over 2 x. Everything's negative down here. We're at negative root 3 over 2, negative 1 half, negative root 2 over 2, negative root 2 over 2, and then negative 1 half, negative root 3 over 2. Over here we're at 1 half, negative root 3 over 2, root 2 over 2, negative root 2 over 2, and then root 3 over 2, negative 1 half. The way that I remember it is I'm looking at like the long, the medium, and the short side. Like the long side is always root 3 over 2. The short side is always 1 half. And then the medium side is always root 2 over 2. All right, that is going to be it for part 2. And then there'll be one more part. I'm going to make it over the weekend so that you guys can look at it ahead of time. And then next week will just be practice tests and...
This is